Hey, everybody. Welcome back for another webinar in our series for DOE Energy Innovator Fellows. And sometimes we have ORISE Fellows joining us. So welcome all. Today, a real treat. We've got a session with Paul Martini on distributed energy resources, but explicitly about how you can take them into account for distribution system operations and tariff provisions that actually make those resources very useful for the distribution system. Paul is someone I've worked with deeply for at least 10 years. He's a contributor to our studies and our technical assistance and training. He's really a leading expert across business, regulatory, and technology dimensions of distribution systems. Over the past decade, he's led development of advanced practices, been a pioneer in how to truly use distributed resources for distribution grid services of value to the system and ratepayers, and also focusing in on provisions needed for tariffs and programs for microgrids. He's worked a lot, not just with us, but also Pacific Northwest National Lab, U.S. Department of Energy directly, a variety of utilities across the country and regional system operators, clean tech firms, and regulatory agencies also in Australia and Canada. And previously, he was at Cisco Systems and served as vice president for advanced grid technologies at Southern California Edison. So it's a real treat for us to have him here today. And as you know, this is really informal. Enter your questions or comments at any time in the chat box. I'll be searching and making sure that we get to your question. And also, you can raise your hand if you want to be called on. You can unmute yourself and ask a question really at any time, but especially Q&A at the end, but don't hesitate. And here's a reminder, and I'll put some links in the chat in a moment. We've got some really excellent webinars to close out our series for this cohort. We've got a real deep dive on something that's super important for regulatory provisions, cost of service studies. So how do you determine the cost causer, right? And how to allocate revenue requirements to different customer classes. It's super important. So we have the same presenter who trains NARUC at the NARUC trainings, trains NARUC members. So that's going to be really great. And that's coming up real soon here on May 20th. On
Lisa,
June,
sorry
yeah.
to interrupt. Sorry to interrupt. Could you go ahead and re-engage the slides? They went back to the original welcome slide there.
This is not working.
No, unfortunately, it's not.
Okay, I will try again.
Okay.
Thank you.
Sure.
Is it working now?
Yeah, great.
Great.
Thank you.
All right, thank you. All right, so June 15th, we've got a deep dive on demand flexibility programs and rates and also load management analytics. This was by request from one of the fellows. So we've got our own Sean Murphy from Berkeley Lab. He's going to present on some work that he's done on demand flexibility programs, including an update that's not even yet released on programmatic responses at utilities. And we've got an expert in the industry, Cisco DeVries, who will talk about what we actually see in the real world, what's working and not working, and how to sort of design your programs around that. And then on the load management analytics, we have Elliot Crow at Berkeley Lab, who's a real expert on this kind of thing. And then Natalie Mimsbrick will round out the set with an update on evolving stakeholder engagement practices for regulatory proceedings. So she'll, this will be broadly applicable, but she'll use as an example some research that we're updating right now on distribution system planning and what's working there. And also we'll have interactive sessions that'll be peer sharing breakouts. I'm also going to put in the chat a link to our brand new cohort with NARUC. So if you work at a public utility commission and you're interested in distributed energy resources interconnection and load interconnection for that matter, come join our cohort. We're running it through September. And you can register for the next meeting, which is on May 27th. And it's on a topic that we're doing research on right now on data transparency for interconnection queues, timelines, and costs. All right, I think that's it. Paul?
Thanks, Lisa. Pull up my slides. Did they come through? Let's see.
Looks good. Maybe you can make them a little bigger.
There we go.
Yep. Thank you.
Perfect. Well, thanks for the opportunity to share some of the research that we've been doing over the last couple of years under the Department of Energy on the question of distributed energy resource utilization. As Lisa said, we've been looking at this particularly from the distribution perspective because there's some particular challenges and some unique aspects to consider when we start to think about using distributed resources. So I'll get into this a little more. So what we're going to cover, I'm going to provide a little context on the distribution system and distribution grid needs. Then we're going to talk a bit about this concept around operational potential, and also provide some background as to why we're focusing on this. And then we'll cover some of the DER solutions for a variety of distribution grid needs, both looking at customer behind the meter resources and particularly in aggregations, but also how front of the meter resources and a concept that we're calling point solutions can play a role too. And then looking at various DER sourcing options, whether we're talking about pricing, that albeit through, say, rates or incentive programs, programs themselves, procurements of various types, and then how do we think about that in a cost-effective sense? And then there's some key takeaways and considerations for regulators, utilities, and aggregators. So in terms of the distribution context, many of us will be familiar with hosting capacity maps and the analysis that is increasingly being done by utilities and required increasingly across the U.S. And as we've seen and noted here, this is an example of Southern California Edison's website, but many utilities have these kinds of maps. When you look at these maps, the green lines are those that don't have any constraints. The orange lines are the parts of the feeder segments that are starting to get constrained, and the red sections are those that are constrained. And as you can see, this gets very detailed. As we think sometimes when we visualize a feeder, we think about kind of the wires on a pole, and we kind of think about it in a more sort of linear fashion. But in reality, there's a lot of branching, as you may be familiar with, and is illustrated in this diagram, that goes on as we then go out into laterals and lateral connections that go off the main line and then into the local neighborhoods and streets, and then to the secondary, the lowest voltage, into serving homes and businesses. So it's a rather sort of fragmented system that sort of branches out from a substation and then really gets much smaller towards the edge. This is important because as we think about the kinds of constraints that are starting to emerge and will continue to emerge on distribution systems, it's because we have more resources at the edge, at the customer premise, that are either consuming, or in the case of solar PV on rooftops or other forms of distributed generation, they may be putting back power into the system. Batteries obviously can charge, but also discharge, and in some cases, those can discharge back into the system. And the same for EVs, as we think about those as a potential load, but in many cases, the cars are evolving towards the ability to also discharge back into the system in the V2G mode. So we have the potential for power flows to kind of move in multiple directions on a distribution feeder. It isn't just as simple as at the main line, where you may have reverse power flow that has been happening for a number of utilities off a distribution feeder back through to the substation transformer into the transmission system. Even if we have that, we have a lot of different flows going on further out into the distribution network itself. So this is where, in this illustration, you see these sort of red flashes and red arrows. This is where you may see some constraints on certain parts, but not in other parts of the feeder and the laterals that come off of that. So this creates an interesting challenge when we think about constraints and where to manage constraints and how to manage constraints using flexible load and what certain types of distributed resources might be able to provide in terms of a service to mitigate the need for upgrades of physical infrastructure. One of the things that's unique about distribution systems, it's kind of obvious when we think about it, but is that as you get further out into the distribution system, the number of customers that are served gets smaller and smaller. Typical substation transformer in a suburban neighborhood may serve 12,500 customers, thereabouts. A feeder itself, there may be 5 to 6 feeders per substation transformer, so that translates into roughly 2,500 customers. The feeder itself is typically broken up into multiple what they call protection zones. That's where we put reclosers to isolate during faults to be able to restore customers more quickly. So you may have 500 to 600 customers in one of those segments, and then a lateral which comes off of the main line to go out, further down into a street to then tie into service transformers that typically you might have 100 to 220 customers on that lateral. And then service transformer itself typically feeds somewhere in the neighborhood of 5 to 10 customers, homes, or small businesses per service transformer. So as we get smaller and smaller, number of customers, this also has implications for the number of customers that may be able and willing to participate in some form of providing grid services, whether it's through a tariff, a time of use tariff, where they're actively participating, or through an actual grid services program, or a procurement through an aggregation. So you can see just a simple, at an example participation rate of 20%, you can start to see if we have these many total customers, this is how many, if you're assuming 20% participation, these are the number that are available. This becomes important because when we start to look at whether we're talking about thermostats or batteries or water heaters or EV charging, the number of customers times the number of devices starts to give you a sense of what kind of capability might be available to tap into for providing grid services. The other thing to consider on distribution, for context, is that not all distribution peaks are convergent with the overall system peak. And this is because what I was showing earlier, where you may have these different power flows and constraints happening as a result of people operating their vehicles, charging them, how their battery may be set up, if they've got that set up a certain way to maximize their solar production for their rate. There may be other loads that are being used at that particular premise and in that area that start to shape a different load profile on that distribution feeder that creates a different constraint and peak at a different time than the overall system peak. So one of the things that increasingly has been identified as a need as part of the distribution planning process is to do this convergent versus divergent analysis to really understand where you can start to look at what we often have referred to as stacked value. So if you have very convergent value, then you can start to see something akin to the waterfall chart down at the bottom left. Whereas if you have divergent, you can see something in terms of value more like what's on the bottom right. So this is one of the things that increasingly is being looked at as part of the analysis to understand how to get the most value out of the distributed resources, first looking at distribution and then overlaying what that distribution need is relative to the overall system peak to be able to understand how to align those. One of the things that we think about in terms of the kinds of services that could be employed at distribution to address many of these constraints tend to be around distribution capacity management, reliability dimensions, voltage, reactive power support, and resiliency. These four have been adopted or adapted in several states, starting with California and Hawaii, adopted definitions similar to this. and other states have as well. There's a standard distribution services contract that myself and team sponsored by DOE put together, and working with the North American Energy Standards Board have developed a standard contract for these services that utilities and others can use. And it uses these definitions as part of that contract. As you can see here, locational value, clearly, these are designed for specific parts of the distribution system or can be used. There are system potential values if convergent on distribution capacity management. For distribution reliability, it doesn't provide system-wide value. That's a very localized potential value proposition. And distribution voltage and reactive power support, that is also very localized. And I should note that when we think about distribution voltage management, that's quite different than transmission voltage management, which is an important consideration. But managing voltage at the distribution does not impact the overall bulk system voltage or reactive power. Resiliency can have overall system benefits depending on how this is done. And typically resiliency to date has largely been applied through services contracts for microgrids. For example, Pacific Gas and Electric has a microgrid in Calistoga that was done through a contract with a third party to develop a microgrid for that community. And that's an example of a resiliency service contract that was put. And that illustrates the in-use dimension. Distribution voltage and reactive power support hasn't been done as a separate contract to my knowledge, or service beyond what has been embedded as a requirement in interconnection standards for adhering to IEEE standard 1547/2018 for certain aspects of voltage and reactive power management. Distribution capacity management has been the primary service that's been used for non-wires alternative procurements in the U.S. To date, and has continued to be. One of the other things that in our research and talking with an organization called Darcy Partners that does custom research on technologies for utilities, they did a benchmark study over the last couple of years on distributed energy resource management systems with utilities. But as part of that, they looked at, in particular, what were the reasons, what were the uses that they saw for why they were pursuing DERMS, grid DERMS on the utility side. This is separate from what the aggregator or others may use in terms of what's often referred to as an edge DERMS that it more directly interfaces with the distributed energy resources themselves. And this is the survey results. I've highlighted a couple of the key aspects in these blue dash boxes. But as you can see on the right-hand side, aside from situational awareness, which is obviously quite important, but in terms of actual use cases, you'll see what they identified as kind of the key use cases that they're trying to address. So flexible interconnections, I'll talk a little bit more about that in a couple of minutes. Targeted capacity management of what I was just showing, primarily through a non-wires alternative approach, procurement, but we'll talk a little bit more about that. General capacity management, that's looking at, say, not through a procurement process, but maybe more through pricing or programs. General voltage management, and with that, I'll touch on that in a little bit too. And then distribution level markets, which is looking at how to facilitate greater participation. And there's been a couple of examples that have started in the Northeast in Connecticut. They had a pilot with a firm called Picklo, but there are a couple of other firms, Electron and Nodes, that have come out of Europe, where they have been using some of these facilitated procurement platforms to try and generate more participation. And there's some experimentation going on now to see if that might also work here. And then you can see what the primary drivers for why, on the left-hand side, why the utilities are pursuing these DER management capabilities. So in sum, distribution is fundamentally different from the power system, bulk power system. The constraints are hyperlocal. They're very much tied to specific feeder transformer circuit segment. The populations are relatively small as you get further out into the distribution system. Contingency options are few if a resource underperforms. As we think about these as non-wires alternative, then the wire alternative wasn't built. So you're wholly dependent on those resources to provide the service that they've signed up for. And reliability failures are very visible and immediate, whether it be outages, voltage problems, or potential equipment damage from overloading that can occur. On the bulk system, as you can see, we obviously are dealing with many more thousands of resources and potentially millions of customers. So you have, much larger pool of resources. So as a result, these aggregations smooth out individual variability where customers may be opting out, or there may be differences as to whether the AC unit is even on, or the car is plugged in or charging, and the like. So you're able to benefit from the law of large numbers as a result. The reserve margins and interconnected system, reserve margins for generation resources, supply resources, battery resources that may be available to bulk system, provide multiple fallback options. So they have a whole process, as many of you are well aware, of thinking about how to have operating reserves to ensure reliability. We don't have that at distribution. And they're starting to apply some of the techniques that we're going to talk about here today around probabilistic accreditation of distributed resources, have a better sense of what to expect from the performance of distributed resources than we've been perhaps doing in the past. So that's really gets us to this operational potential for distribution. And what that is really speaking to is that when we do distribution resource potential studies, or the value of DER kind of studies, typically what we do and what's involved is looking at addressable potential and also the achievable potential. And by addressable potential, we mean all the DER that are physically present in a service territory, or could be expanded through some means in terms of what adoption rates might be, but that's really a theoretical sort of maximum. The achievable potential takes it one level down in terms of refinement, and it basically looks at the subset of that, the portion realistically reachable through rates, programs, contracts, giving customer behavior and market limits. So really looking at the kinds of factors that, whether or not you can, entice a customer to participate, or, the kinds of outreach that's necessary, and then the reinforcements through incentives and other reinforcement to help a customer, reach the potential of what might be here achievable. That is all well and good, but that doesn't translate specifically into what operationally might show up at the moment that the distribution operator needs it. And that's where we've had a gap in the industry, is that, and as you may be aware and experienced, often we have these studies that have been performed, and yet the distribution planners and the distribution operators haven't really bought into, what the DER might be able to provide. So what we're focused here on is, how do we close that operational value gap? So we know that there's a value that can be achieved, but we need to take it one step further in terms of analysis to really look at what can reliably be depended upon with high confidence to meet a specific need at a defined location and time. And this is what we refer to as operational grade value. So it's really the third level of this analysis that we're going to talk about here next. So obviously, it starts with the customer, because in this case, we're largely focused on behind the meter resources. There are other factors to consider when we think about front of the meter resources that are specifically for designed for grid purposes. But when we think about behind the meter resources, the devices that customers have bought were typically bought for their own purpose, not to serve the grid. So obviously, understanding the factors that go into both how customers will be using those resources, as well as their willingness to provide, residual, value, if you will, beyond what they're using it for the grid, are very important factors that come into play. Now, obviously, when you do an availability analysis, you're incorporating elements of this, but this extends it further into really trying to understand from an operational standpoint the so what of that. And that's what we really get into. So, how do participation rates, opt-out behavior, and not just opt-out behavior on an average, but what does that really mean when we talk about potential opt-out behavior during an event? Which obviously there's data that can track this, and how do we analyze the data from actual program performance or contract performance to really understand and improve our estimation techniques? How do we really understand the limits on customer fatigue as it relates to an operational standpoint? How do we understand the dimensions around EV charging and so on? So many of these things have been incorporated into program analysis I've described before, but there's another level as we're discussing that we really need to take into account when we think about from an estimation standpoint, really kind of reducing this a little bit in terms of being, the dependability and the reliability of that based on statistics. So what I mean by that is if we look here, one of the things we want to be able to do is understand what is the typical behavior of a device when it's being operated for a grid service. And here's some examples. So when we think about a behind the meter residential battery, let's say it's a 13 kilowatt hour battery, that would, let's say, typically might provide 2.5 kilowatts over a 4-hour period. And so obviously you can see the reduction in blue that you might get. But obviously you have to take into account when you're going to recharge that battery and what timing. Here it's kind of just simply shown that it's charging before it's discharging, but that can obviously be shaped differently, and you would want to think about that as part of this analysis. An EVSE, you might be able to get 1.2 kilowatt hours, over a 6 to 8 hour period. And again, you'd want to understand this dynamic and how this would operate, and whether or not you'll be able to get the 6 to 8 hours as we think about it. And then smart thermostat, water, heat pump water heater. The interesting part about a smart thermostat is that it has a bit of a sawtooth dimension, which is you get an immediate drop, but as the temperature starts to rise on average, you start to see a degradation as the HVAC starts to kick back in. So you get more of this on an individual device, you start to get this kind of behavior. So it's really important to think about how you group these resources together into a cohort that start to mitigate some of the issues we're talking about, some of the snapback factors when you're charging or recharging, or it comes back on, that you can see and probably familiar with typical demand response programs, but also these opt-out kind of impacts that may happen during a period, as well as this sort of smart thermostat sort of sawtooth effect. So you can stagger these into a cohort so that you get more of a levelized performance. What's shown here in terms of these numbers, like for batteries roughly 20, EVSE roughly 50, roughly 100 for thermostats, and 50 for heat pump water heater, is that when we've done some of the initial statistical analysis, these numbers are sort of the minimum number of devices that you would, for that particular type technology, that you would need to start to do some statistical analysis. You can start to get some levelized performance that is consistent with these figures, and you could smooth out the smart thermostat from more of this triangle shape into something that's more flat. And that's why when we start to look at these small populations, going back to what I was showing earlier in terms of the number of customers that may be out in parts of the distribution system, you really need to look at this, very specific technology, and in some cases, the actual manufacturer of the technology. So there's quite different performance between one manufacturer's smart thermostat and another manufacturer's smart thermostat. And so really understanding those differences, because as you start to put them together or group them or understand how you might put these various cohorts together, it's an important consideration. And then again, if you're starting to match one technology, let's say a smart thermostat portfolio with a heat pump water heater, or then EVSE or battery, each of those have quite different characteristics that you need to understand how you would put those together in a way that you get the overall performance that you're looking for. And that's really what this gets into. And that's quite different than when we think about it at the bulk system, although they are moving also to technology specific analysis. It's really important here at distribution because you've got smaller portfolios that really don't average out at scale like you do at the bulk system. So just to illustrate this a little more, as you can see here, when you have a larger population on distribution, let's say at the substation transformer, you get the blue line on the left in the chart, where it's a little bit more predictable, dependable performance. But if you have a small population, let's say further out in the feeder, let's say it's out in one of those feeder segments, or maybe on a lateral that you have this participation, now you have a performance characteristic that looks more like the red line. And these curves, by the way, were developed off of some actual performance data that we had from some DER programs. And so it just illustrates this point that we need to start thinking about certain levels of devices that you can start to get some more predictable or at least probabilistic kind of response that you can start to depend on. So when we're at very small, for smart thermostats, at smaller levels of groups of smart thermostats, you have highly stochastic behavior, more like this red line. As you move into the emerging probabilistic, you start moving more towards the blue and obviously more deterministic. At larger numbers, you get more of this blue line too. So the idea is that you want to start trying to think about how you do groupings, at least at this emerging probabilistic level, if you're going to try and do aggregations. Now, that doesn't mean you don't try to do something at the edge on the individual device and the individual customer premise, and I will get to that in terms of what we refer to as point solutions. But in terms of aggregations, these are, you really want to be starting to look at, how you can start to identify more probabilistic behavior that you can start to plan towards. And obviously, ideally you get to a more deterministic outcome from a planning and then operational perspective. The other concept that we've teed up in our work is this idea of adding planning reserves, distribution planning reserves at the in the distribution planning process, recognizing that just like at the bulk system, nothing ever works perfectly 100% of the time. And so as a result, you need to have some reserve to ensure that you have the reliability you need in the event that something happens. And so the thought is that you can, through this probabilistic approach, you can determine how much reserve margin you need. It's similarly to the way we do it in the bulk system, where we look at a confidence level that's like at the 90th percentile. So not 100%, but say at the 90th, and the average, which is the 50th percentile. And you subtract the two, and then that kind of gives you a sense of how much reserve you might need. So that might yield, for example, an additional 10% that you might need over and above what 10 to 15% that you might need. Now, the example that's on the right tries to illustrate this in a practical sense, in that we looked at an actual procurement by a utility in the Midwest, and they had in their contract for a non-wire alternative, they specified that there was a minimum performance requirement of 90% before financial penalties kicked in. Although they contracted for 100%, the penalties only kicked in at 90%, which meant that it's quite possible that the performance under that contract would only reach 90% on a regular basis. And so you need to cover that 10%. And then on top of that, you'd need another 15% based on the probabilistic analysis. So that's what those two red stacks are that add up to the total amount that might be needed. Now, the other thing that we note is you really want that from another provider, not the same provider, so that you've got some additional assurance that there is the backup that's there when it's needed. And that reserve can come from a variety of different kinds of resources that might make most sense depending on what the need is and what might be available cost effectively. What I've been describing as this, what we've been referring to in some of our more recent work on distributed resources is also known as grid edge resources. So the same concept. This operational potential, what I've been describing here, this is illustrating a little more of the detail that you would go through in terms of steps. And this follows the achievable potential, which is tied as an extension off of the distribution grid needs identification process. That's part of the distribution planning or integrated distribution planning process. So the flow goes from you identify the grid needs, then you do this achievable potential study, which has typically been done, and then you would take that information and feed that into this operational potential. And from there, then you go into your sourcing approaches and how you're going to orchestrate those, control them, or whether there's aggregators involved or other entities involved in terms of being able to operationalize those services, and then the actual operations, and then a feedback loop that goes back into the process. There's a forthcoming paper on this overall approach, and there's more detail about how this would work in practice. So there's, just to sum up what we were just describing here for the last few slides. So we characterize the technology-specific performance, and this is, really based on observed data and energy engineering considerations. So understanding building types and are critical factors that go into this. Model the full range of outcomes using a Monte Carlo simulation to do the probabilistic analysis that we described. You want to target a performance level, let's say 90th percentile, that you need to be able to do that. And then you can start to affect or determine what sort of reserve that you might need from your planning standpoint that you then source and then is available as needed during the operational perspective. We did identify that in one or two utility NWA contracts of late, just in the last couple of months, that it looks like there may be a couple that are starting to head down this path, but without a specific, clear sort of analytic, quantitative analysis approach yet. But clearly, I think the feedback we've gotten from a number of utilities is this is something they recognize they need to probably be doing as they move forward with the greater utilization of DER.
Paul, before we go to this next section, I thought it might be a good time to just check in and see if anybody has any questions. You feel free to, we're a small group. I think you could just take yourself off mute and break in here. And while people are thinking, I have a question for you. Mm-hmm. Emily, I don't know if Emily has a question or is just happy with the information, but appreciate it.
I'm just giving a thumbs up.
Great.
Thanks, though.
All right. I have a question about, we've been doing, when I say this, considering reserves and, things don't go always like they used to, or you expect them to. So can you sort of do a little bit more compare and contrast this reserves approach, at least, and the probabilistic analysis and the Monte Carlo analysis, which I guess same thing, with what we do in the bulk power system for, say, integrated resource planning historically? So, and how it's different also. How it's the same and how it's different.
So I would say that this is similar. So this probabilistic analysis and using a Monte Carlo techniques to do that is something that has been done in integrated resource planning for many, many years, decades. And so in concept, it's similar. What is different is how we're treating the performance of distributed resources within that analysis. So, what we've done in the bulk system that's some of you may be quite familiar if you're familiar with integrated resource planning is there's an accreditation process for generation. So when you look at a particular, we don't treat all generation the same. So solar is factored differently than wind, and say a nuclear plant versus a natural gas plant versus a coal plant, and even each type of or generation of that plant, has different reliability factors, different performance characteristics. All of that is taken into account. So, and that's called accreditation. And if it's hydro unit, there's something called project dependable capacity based on hydrology studies to think about what's the minimum amount of energy that might be produced based on sort of worst case, hydro year. So there's all these kind of factors that go into it. We haven't really been doing that for distributed energy resources. And I think we're, certainly one of the things in the paper that's forthcoming is we've actually looked at what all the RTOs and the regional transmission operators and the independent system operators are starting to actually look at a similar approach to DER accreditation, but for the bulk system. And here we're looking at this at the distribution. So that same concept that Lisa, as you're asking, at the bulk system, we've done for other forms of generation and batteries for bulk system. We're now starting to apply that for distributed energy resources. And in particular, what we're focused on is what is the implication of that for distribution, because you don't have these large numbers. So you may have the same performance characteristics of people opting in and out and whether the device will be on or not based on temperature and building type and all that. What's different at distribution is now we've got smaller populations to work with, and what's the implication of that as we start to put these together. So that's, I don't know if that helps, but that's what's different here.
That's great. Anybody else have a question? If not, we can move on to sourcing.
Okay, so when we refer to DER sourcing, we're referring to the options to basically engage and compensate or incentivize customers to provide distribution services. And this could also be for bulk system services too, but here we'll talk about distribution for customers to provide distribution-based services. And so that really involves pricing programs and procurements, and we'll get into this a little bit. And also, well, I'll touch on this in a second. But so one of the things that I think it's important, I touched on this early on, is that there are really sort of three classes of solutions as it relates to distributed energy resources. So one is front of the meter battery or distributed generation that might be contracted for, or in some cases utility owned. So those are also distributed. So these are ones that are connected at the distribution level, but different than bulk system. And so there's a summary there. Typically, that's done through a competitive procurement, approach. And then we have customer DER aggregation. These are customer behind the meter resources. They may be existing resources that they're, they bring your own device, or it may be as part of a program to get more or incentivize more devices to be adopted. But both of those dimensions are underneath this sort of aggregation class. And a lot of what I was discussing earlier was around this customer DER aggregation. The other is a concept that we teed up, which calling point solutions. That is where you have really low-level needs in the distribution system, whether we're talking a service transformer, let's say a service transformer. Really thinking about trying to do an aggregation there doesn't really make sense, because you only have, say, 5 to 10 customers. And of those, if you only get 20, 30% of them, you're only going to get, 2, 3 customers that might participate. So that may or may not be enough, but it isn't something you really think about as an aggregation. Here, we can start to think about something around what you're trying to do is modify either the use of energy or the output of energy in such a way that it mitigates the need for or creates the constraint and mitigates the need for any upgrade. So that is, if you've got an EV that is otherwise might overload the service transformer, the charging of that EV. You can use a EV time of use rate that the customer then changes how they, charge the car, and therefore it reduces the loading on those transformers such that there's no more constraint. I mentioned that because EV TOU rates, as I understand it, have been extremely effective and provide a very, relatively low to no cost option to basically mitigate a service transformer overload. Now, it's not the total solution if you've got everybody in that, on that service transformer that to have an EV and, need to charge. You're probably still going to have to think about something other than, doing that, but it can certainly mitigate when you need to perhaps change that service transformer. But this idea of having a point solution can be quite cost effective. The other thing is that we've done in several states is, we had these problems with voltage issues where when rooftop solar came in, it was starting to create voltage rise issues where, they were getting, the voltages were getting out of the standard frame parameters and having violations. So, there was an issue about trying to manage voltage. The inverter standards and interconnection standards have adopted the IEEE standards such that most of that has been diminished or has been significantly mitigated. So that's another thing that's a point solution. You're dealing with the issue right at the point at which the issue is being created. The other thing that's been developing here recently in the last 2 years are these flexible connection agreements, both flexible interconnection, but also flexible service connections. The flexible service connections have been largely used for fleet charging facilities, public charging facilities, where they agree to not exceed a certain limit on the consumption for that facility, which mitigates the potential overload and constraint that might otherwise be and cost to upgrade that might be otherwise required. Same thing on the interconnection, adjusting the output of that system, that solar or wind system that be connected to, sub-transmission or distribution substation that otherwise would create a reverse power flow issue can be mitigated through these flexible interconnection agreements. And so these are things that are starting to be used. Those are point solutions.
Paul, there's a question.
Mm-hmm.
Any thoughts on whether electric vehicle time of use or peak demand structures are more effective for this issue? Peak demand structures, not sure. Maybe Isabel, you'd like to clarify. I'm not sure if that's a programmatic response as opposed to a rate. You can take yourself off mute or, peak demand tariff. Adding a demand charge. Okay, so this would be like, presumably like for a residential customer, adding a demand charge to the standard electricity bill as opposed to just volumetric versus a specific time of use rate for EVs or third option, a general TOU rate.
Yeah, I'm not a rate expert, so what I can say is that demand charges have been extremely effective in the commercial space, but over the years, at residential, I'm not that familiar with.
Yeah, they're not something that typically, say, a utility consumer advocate for residential would favor. There's a lot of arguments around that.
But this is, I think, one of the things that folks are starting to look at is, in generally, when we think about rate design, for DER and including EV, is starting to think about for consumer, are there other rate structures that start to account for both the value and the underlying electric service that they would be consuming when they're not, leveraging their own resources, let's say. So how best to think about that rate design, I think, is an open question that people are examining. Some of the work that, for example, states and some utilities like SMUD looked at this, and some states like New York and others, Hawaii, that were looking at these value DER type tariffs, how those may be adapted. Many of them were in the case of New York, was more about a front of the meter type resource, as more like a feed-in tariff. Hawaii had one that was more around point solutions for individual consumers to sort of encourage, shaping the usage a certain way to minimize the need and also encourage battery adoption. Obviously, we've had in California NEM3 that has done something similar to encouraging battery adoption to go with the solar. So there's ways to think about that, but I think we're still on that journey to figure out what works best.
And I put a publication in the chat that we did with the Brattle group, pretty recent paper on rate design. Quick follow-up question, so quick response. Any advice on point solutions for areas that don't have robust advanced metering infrastructure?
Well, it depends on what the issue is. So if we're talking about if the issue is voltage problems from rooftop solar, then you don't need AMI for that. It's basically adopting IEEE 1547 as part of the interconnection standard. If you're looking at the issue is public charging of public charging facilities for EVs or fleet charging, again, you don't need AMI. If it's fleet charging, they'll have something. They'll have commercial or industrial type metering technology involved, which is not AMI. That's more small commercial.
And there are also solutions that aggregated DER aggregators or flexibility aggregators have that don't require AMI. So they'll provide the technology, and they'll have another way to get the communications.
You can get the data. The question is, do you have the time varying, the time differentiated measurement for revenue purposes for settlement? But outside of that, Lisa's
well,
right.
for program, just in terms of programmatic, we don't have to worry about that, right? If you have a program, a demand flexibility program of some sort, DER aggregators don't necessarily need any of that.
Typically for settlement, they do because you got the baseline and all of that you got to figure out.
It depends on control. I mean, if you just give them access to control your thermostat, there are other ways.
But the settlement process is where you start to look at having, but it doesn't have to be AMI. It can be
right. That's what I mean.
Else. You just need a time differentiated meter. The thing on this slide, and I know we're running out of time, but what I want to emphasize on this slide is that not all sourcing methods have the same impact in terms of ratepayer costs. So this tends to get overlooked, I think, through some of the discussions in the industry. But when we think about a tariff or rate, price signal, this is relatively low cost to implement, largely billing changes and customer communications to roll this out. But this is relatively inexpensive relative to some of the other options. When we have demand side management programs or DER programs, demand flexibility programs, if those existing that may be funded through, say, a customer charge on the monthly bill, to the extent that those programs can be redesigned, redirected towards more geo-targeted and temporal needs for addressing some distribution needs, or particularly as it may line up a little better with the convergent aspects that we touched on earlier, then really there's really not a lot extra cost there from a ratepayer standpoint incrementally than what they were already paying. When we get into procurements and bilateral contracts for DER, non-wires alternatives, the classic what people have been pursuing for the past 8 years, these are incremental. Typically, the cost is capped at what it would have cost for the deferred value or avoided value of the distribution infrastructure. But that distribution infrastructure was incremental. That was going to be new costs that ratepayers would have been bearing. So using a non-wires alternative, the cost to provide that is also incremental to what otherwise was in the in rates. And then the local flexibility market is kind of a unique thing because of the way it basically is as I mentioned before, it's an alternative way to doing procurements to try and reduce the transaction cost and for market participants and getting more. But basically what you're doing in these markets is basically signing bilateral contracts. The other thing about these markets is, although they provide a platform as a service option, they get a transaction cost. So for every contract that's signed, there's usually a 2 to 3% transaction cost that goes with it. Now, if there's large volume, that probably gets negotiated, but this isn't inexpensive. This would be an additional cost. Now, there's some cost savings in the way that they potentially for the utility, because they can manage some of the back end contracting and some of the other elements that the utility doesn't have to pick up, but it is something to think about. One other thing to touch on perhaps is that we are seeing a fairly significant change in the aggregator or virtual power plant service provider market. This comes from a Wood Mackenzie study that was done and survey last year that you may be familiar with. And what we're seeing is, both a change in terms of who are aggregators. So the number of independent aggregators have largely been has really changed. A number of them have exited the market over the last 4 or 5 years, and several prominent ones last year. And so what we've started to see is that there are more hardware-based firms such as Tesla and Nest, although through Renew Home, and but it's kind of affiliated with Google. So, and then a lot of the autos and some others have kind of been more directly involved in the aggregation. So there's kind of a different mode here. And what we're also seeing is that even those independent aggregators that are still remaining, there's much more of a focus around partnering type relationships that would sort of typically how we think about how programs are done and program administration roles are. And there seems to be more of a move to that. There is some suggestion that a VPP tariff, in fact, there was a group of aggregators who put forward the concept of a national VPP tariff, again, with the idea of trying to reduce transaction costs, try to create a more level field in terms of risk sharing, in terms of the development and operation of distributed resource solutions. So there's some interesting moves here that are going on that are a little different than where we were 10 years ago in terms of thinking about how these would be sourced and who would be providing the service. I'm up at time. This slide is talking about flexible interconnection and service connections. I don't really have a lot of time to go through this. It's here. There's some good papers available for this that we can point you to as well. Here on this slide, this is an example of how you might think about where the need is, the type of need, and the kinds of solutions that you might think about that would apply, the categories that could apply, or in a combination. So it isn't just one, you could have a combination of these. And I don't get into all the details of, specifically what kind of behind the meter customer VPP, for example, but what each of these might comprise. But they're specifically looking at, there's certain things that you might do, but other things you might not include it. So if it's not listed, it's sort of like the type of solution, then it's considered that it really wouldn't necessarily apply. And again, that has to do with the number of customers and where it's located on the distribution feeder. But this gives you just an example of how you might apply that. In terms of overall takeaways, I won't go through all of these, but here's a set, thinking about some of the key things that, regulators might think about, and other policymakers, what utilities might think about in terms of how they would approach better utilization of DER distribution, and also for DER aggregators or VPP service providers or that would be providing these services. So how best to think about the kinds of things to move forward and get greater utilization of these resources for distribution. And thank you.
That was great. We have one question here if you have time. Here's Lucas saying, I appreciate your point about DERs that serve a small number of customers or a small segment of the distribution system. And, that those kind of options can lack contingency, options and could be higher risk. A front of the meter solution has the benefit of utility control to provide more assurance under these cases, like a large battery, say. But how would you address this issue with aggregation or point solution sourcing options?
The way I look at it is that you look at the combination that gets you there. I mean, if you can get the reliability or the performance you need through point solutions, and again, you're looking at historical data, you're really understanding the performance. These questions that were asked about, EV time of use versus some other form of a structure that might be used. If that can get you the results you need, that you could stop there. If that doesn't get you all of what you need, then you can start to look at, well, okay, maybe it's not just the service transformer. That if I've got an overloaded the service transformer, and I also have probably a constraint that's on the lateral. So then at that lateral, now I got more customers. So how do I deal with that? Maybe I do change the transformer because that's a $5,000, $7,500 proposition. Okay, that's not that expensive, but I got to deal the lateral because now you're talking about a couple $100,000. So now I can look at some other options that maybe are more cost effective in terms of aggregating and or something front of the meter that might make sense on that. Or, now we're into the line segment and now maybe a front of the meter battery in addition to some aggregation. But again, as I was pointing out, there are different incremental costs with every one of these options. So to the extent that you can start with what can you get out of the lowest cost options and then work your way up into the next best option to the next best option to get to the performance you need. This is essentially going back to something you mentioned, Lisa. This is how you do a resource stack in bulk system. It's the same concept here. Right. So start with your lowest cost resource and then work your way up. It may be that not the most firm, if you will, in terms of what you might get off a TOU EV rate versus a battery, a grid control battery. But that grid control battery is the most expensive option. So can you work your way to something that gets cost effective and mitigates the need and do it at a cost lower than what the grid infrastructure investment would have been?
And the diversity of loads and generators works in your favor. And just like for bulk power system, you need reserves. You need to buy more. You can't just buy the exact amount that you need. All right. Well, that was really great, Paul. And thanks so much to everybody who stuck with us. And we'll look forward to seeing you soon for the next webinar.
Thanks, everybody.
Thank you.